Hey guys, so in our last video we did talk about momentum and impulse. So in this video we're going to talk about the conservation of momentum. So before we can start, don't forget to hit the subscribe and also the bell button if you want to get notified when I post the videos next time. So as I have promised that through my course I'm going to do theory and then examples, and then after that past papers. So by now we're still on the theory and examples, then after these we're going to go to past papers. So today we're doing conservation of momentum. So before you can tackle any problem from a conservation of momentum, you must understand what's a system. So I did talk about a system in our last video. You must understand first what's the system. So I gave you examples of if you have 1, 2, 3, 4, 5, 6 objects. A system actually is just a group of objects that we can separate in our mind. So if you have many objects, but there are some of them that you can separate in your mind, or you can just put a boundary in your mind for those objects, then we call that a system. So this here we can just take this as our system, these 4 objects as a system. So anything surrounding the system is called environment. So anything surrounding the system is going to be environment. So a system can be one or more objects one or more objects that we can group together. So that's a system. Again, on top of understanding the system, you have to understand what isolated system. So what, because for the conservation of momentum we're going to talk about the isolated system. So you have to understand that what's isolated system. Isolated system. So this type of system, if you watched my last video, I said is a system where we don't have any external force acting on the system. So here, no external force. I will just write no external force. So my question again is, it's what's external force that I'm talking about. So to understand that, let's take a look of this one. So if you are dropping a ball, let's say this is a ground, and then this is the ball falling down. So if you drop this ball while the ball is falling, what's causing the ball to fall is a force of gravity. So if you take your system as the ground and the ball, therefore there's no external force acting on the system, because your system is this one, is this, and then and this. And what's calling the force, the object to fall, is the force of gravity, which is within the system. So if you say your system is a ball and a ground, then you don't have any, this system is isolated. Let's consider the same condition. Now have a ball and the ground, but your system now, you take the ball only as a system. So if you take the ball only as a system, as the ball is falling down, what's causing the ball to fall is a force of gravity, which is acting, but it's acting outside the system. It's not inside the system, because in our system we have a ball only, but this ball is affected by one force that's not inside the system. It's an external force, so we call that external force. Therefore this system is not isolated. This is not isolated, and then this is isolated system. So that's the difference between isolated and a isolated system. So we're going to after understanding the difference between isolated and unisolated, we have to come to the law of conservation of momentum. So now we are going to state this law. So we're going to state this law according to the system. So this law, remember that we proved momentum, we defined momentum in our last video. So we said that momentum is a product of mass and velocity. So if momentum is a product of mass and velocity inside the system, so if you have a system, and then in this system, let's say you have a certain objects, you have objects in this system, you have objects, you have two objects, you have this one, you have A, and then you have B. So they are moving in different directions, and then at a certain point these objects they collide. So if they collide, this is before, let's say this is before the collision happened, and then we're going to have a condition where it's after. So let's have another one here, and then let's say this is a condition after. That was a condition before, then let's say this is after, then this is a condition after. So here you still have the same balls, but now they're moving to different directions. So this ball A now it's moving to this, and then this ball B now is moving to this side. You see these objects, they change the direction, doing whatever, even they can change the speed, whatever they're doing. But if they're inside a system where we have no external force acting on that system, therefore the momentum of this object, if we take the momentum, which the momentum of this object is mass of this multiplied by velocity, and mass of this multiplied by its velocity, is going to be the same as momentum of this one. As we take the mass of this one, we multiply by velocity, and we add with the mass of this one multiplied by velocity, regardless of the change in direction of the velocity or the change in magnitude of the velocity. Because if these two balls collide, the velocity is going to change, everything's going to change except the mass. So even the direction change, the velocity change, but one thing that you have to keep in mind, momentum of these objects, momentum here, let's call this is going to be pi. Momentum here, p initial, is going to be the same as this one, as momentum here, p final. Okay, so this is what we're going to call a conservation of momentum, because the momentum initial in the initial state is going to be the momentum in the final state, regardless of what's happening within the system. So whatever it's happening there, as long as if there's no external or any force that's coming from the environment to a system, therefore we're saying that the momentum will remain the same. So if p initial is the same as p final, we are saying that the momentum is conserved. That's why we have a law of conservation of momentum. So you can state that by linking the ideas that I told you. So we can state that by saying in an isolated system, the total linear momentum is conserved. Momentum is conserved. Okay, so this is it's a law of conservation of momentum. So now just going to write the formula actually of how can you put this in terms of equations. So in terms of equations, that's going to be easy, guys, because as we said that the total linear momentum is conserved, and the momentum of here of the momentum before the condition is the same as the momentum after the condition. So let's just write the momentum before the condition. The momentum before the condition, which is pi, is going to be, remember that we have an object A, so it's just the mass of A multiplied by velocity initial of A plus mass of B multiplied by velocity initial of B. So this is a momentum initial. So there's a momentum for this one before. So the momentum after is going to be the same. It's going to be momentum of A multiplied by velocity final of A plus momentum of B multiplied by velocity final of B. So how can you put this, since we said that the total linear momentum is conserved? So therefore, meaning that the momentum initial is the same as momentum final. So this, remember that this is the sum of these momentums. So we can just say sum of momentum initial is the same as sum of momentum final, because we was taking the momentum of each and every object that it's within the system. So if this is the case, therefore you can rewrite that by saying that mass of A multiplied by velocity initial of A plus mass of B multiplied by velocity initial of B is equal to mass of A velocity final of A plus mass of B velocity final of B. You see that? So this is an equation that we are going to use throughout momentum. This is a very useful equation. So if you forget this, you're screwed. You don't have to forget this. You're a child, guys. So this is a very important equation. So we're saying that the sum of momentum initial is equal to the sum of momentum final. Why? Because we stated that in a isolated system, the total linear momentum is conserved, meaning that the momentum initial is equal to momentum final. And this doesn't mean that each and every time you're going to summarize, you're going to take the momentum of A and B. No, that's not the case. Sometimes you might have more than 3 objects. That means you have to add with that object again, mass of that object C plus velocity of C, mass of that object which is D plus multiplied by velocity of D, just like that. So it's not like it's always gonna be like this. It's going to depend on the objects that you are dealing with. So okay, so now let's move on to example of law of conservation of momentum. So here we have this example here. It says that cat B of mass 350 gram moves on the frictionless linear air track at 2 meter per second to the left. So it's moving to the left, so it's moving to this direction. So let's say we have this cat, which is B, it's moving to the left, so therefore it's moving to this direction. It's moving to that direction with 2 meter per second, and the mass of these are going to divide that by 1000 because it's in grams. Then we have to convert to the physics SI units, which is it's kg. So this is going to be 0.350 kg. Then says that cat B strikes cat A, so therefore that's a collision. So this, you have cat B here, you have this is B, and then that means A was here. So let's get the information of A. Of mass 200 gram. So the mass for A, this is for B, and then the mass of A is equal to 0.2 gram kg. I converted that already. Traveling in the opposite direction at 1.2 meter per second. So it's traveling to opposite direction. That means it's going to this direction with v initial of a which is 1.2 meter per second. So after that, after the collision, cut B continues in its original direction at 0.7 meter per second. So after the collision, this was before. So after, what happened? After the collision, 1 didn't change the direction. So B, after the collision, B is still moving in this direction. But we don't know about A. A is here. We don't know about A. B is still moving in this direction with 0.7 meter per second. So that's the velocity final for B. Velocity final for B. But we don't know about the velocity final for A. So that's what we're going to do to try to calculate. So let's read the question. Why is this considered an isolated system of colliding bodies? So why this system is isolated? Can you tell me that, if you have been listening? Why this system was saying this system is isolated? Because we are told that this is a frictionless linear air track. In a frictionless linear air track. So that means we don't have any external forces. Only these bodies are considered as a system. So only this object A and object B are system. No external force or no friction, because we have no friction. We have no friction. No friction. Because we have no friction. That's why I was saying this is an isolated system. The second question says calculate the velocity of the car A after the collision. So here we must choose the direction. So we're told that this thing, the second card is a card B of mass 350 gram. It was moving to the left. So since the initial direction was going this way, we can take left as positive. So let's take left as positive. Let's take left as positive. So this is the first thing that you must do. First, you take the direction, you choose the direction so that you want to take as positive. You can take right as positive, or you can take left as positive. So as we defined, or we stated the law of conservation of momentum, we said that the total linear momentum in an isolated system is conserved, meaning that the momentum initial, the sum of momentum initial is the same as the sum of momentum final. And here we have an object A, which initially it's going in opposite direction with the object B. So one is going to be negative while another is going to be positive. So this is the same as m of A v final of A plus m of B v final of B. So therefore here we want the m of A. M of A were given all of these things. So they gave us the mass. So the mass of A was 0.2. So the mass of A is 0.2, and then they gave us the initial velocity of A. But remember that the card A was moving in opposite direction with the card B. If you can go back and read here, if you can check, it says that of mass traveling in opposite direction of at. So was traveling in opposite direction with velocity of 1.2. So the velocity initial for this one is going to be minus 1.2, since was traveling in opposite direction. Then we add with this one, which the mass of this one is 0.35. We multiply by its initial velocity, which was 2, and then final mass of A, it doesn't change, is 0.2 still. Final for A, are we given that we're only given the final for B. So final for A, that's what we're looking for. Yeah, that's what we're looking for. V final of A plus this of B, which is going to be 0.35 multiplied by, since it's going in the same direction to the original direction as the set here, as the set they specified that this is going in the original direction, so it's going to be positive. So when we take this to this side, it's going to be negative, so we can just punch a calculator to get the answer quickly. So it's just 0.2 multiplied by minus 1.2, you add 0.35 multiplied by 2, and you subtract 0.35 times 0.7. So we get, when you take this to this side and then you punch this in your calculator, you'll get 0.215, which is equals to 0.2 V final of A. So you can see that here, from here it's easy, you can just divide both sides by 0.2. So when you say divide by 0.2, you get V final of A is equals to 1.075. So therefore this finally velocity, the object A, it's going in a direction of cut A, it's going in opposite direction of its initial velocity, meter per second. Never forget the units. To the left, because it's positive, to the left, because it's positive. So it changed the direction. Initially it was going to the right, and then now it's going to the left. Finally it's going to the left. So the last one says, how does the change in momentum of each card compares? So we want to check the change in momentum. What's the change in momentum? The change in momentum of each object. We're going to start with the change in momentum of A. It's going to be P final of A minus P initial of A. So the said hint, use calculations, don't guess. So the change in momentum for B is going to be P final minus P initial. So you can see that here for this one, the change in momentum for this one, we're going to take the final one, which is this. We have a velocity here. So this is for A. So we're taking the final one, which is what we have the mass here for this A, which is 0.2. We multiply it by 1.075. And you subtract with initial was 0.2. Since was going in a negative direction, therefore inside is going to be a negative 1.2, because this was going in a negative direction. So that's going to give you the change in momentum for A. So the change in momentum for A is going to be, when you punch that on a calculator, multiply by 1.075 plus 0.2, 1.2, you get 0.55. Remember, don't forget the units. So the units is kg meter per second. So let's do the last one. So the last one is going to be momentum for the change in momentum for B. So change in momentum for B, which for B is going to be mass final, which mass final was mass still this multiplied by the velocity final. Masses will stay the same, will never change. Multiplied by velocity final, which was 0.7 minus initial. So initial, this thing had 0.35 multiplied by 2. So since the direction doesn't change, the signs remain the same for both velocities. 0.7 minus 0.35 multiplied by 2. So for this one, the change in momentum is minus 0.455 kg meter per second. So you can see here that the change in momentum for both objects are the same. So here, change in momentum and change in momentum, those changes that happened inside the system, each and every change that happened there is going to result to the one thing. So even if you have 100 objects, so this one changed the momentum and also that one changed the velocity, but the momentum is going to be the same. So you can see here that the change in momentum is the same, but it points in the opposite direction. So therefore, this proves again that the law of conservation of momentum is true. So momentum initial is equals to momentum final. That's why the change in momentum for these objects, since they were in collision, therefore the change in momentum of each and every object must be the same, only if the system is isolated. So the set how they compare are the same. Those momentums are same. The momentum initial and minus momentum final minus momentum initial, and for A, and momentum final minus initial of B, they are the same.